Hello everyone. We had this problem posted in methodology uh, where n is equal to 1 to the power 1 factorial plus 2 to the power 2 factorial up to 2017 to the power 2017 factorial, and we needed to find the remainder when n is divided by 45. So this is a good application of Euler's theorem, and I mean it can be done without Euler's, but Euler would definitely reduce the calculation. So if we check first of all, 45 is equal to 5 into 9. This is pretty obvious that we need to check the remainder under 5 and under 9, and we have to combine the remainders. There is a direct approach, but I believe that would be a little lengthier. So this is a shorter method. Now, first thing, let us figure out the Eulers of 5 and 9. So the Eulers are 4 and 6 respectively. I'm not going into calculations of Euler. You can check some other videos and all. So Euler's of 5 is 4 and Euler of 9 is 6. So first of all, let's try and figure out the remainder when n is divided by 5. So according to Euler's theorem, a when raised to any multiple of 4, 4 being the Euler of 5, when divided by 5, will leave a remainder of 1 when a is co-prime to 5. Or simply put, a is not a multiple of 5. And if a is a multiple of 5, the remainder should be 0, because if a is a multiple of 5, any power of a is a multiple of 5, right? So there are just two scenarios. Either the remainder is 0 or remainder is 1 when the power is a multiple of 4. Now if we check the powers of 1 factorial, 2 factorial and so on, 4 factorial onwards, 4 factorial, 5 factorial onwards, every number is a multiple of 4, right? So all we have to do is, 1, find how many multiples of 5 are there. 2, find the first three numbers remainder separately, because those are not having powers which are multiples of 4, and everything else will leave a remainder of 1, right? So first thing, how many multiples of 5? So from in 2017, 1 to 2017, the number of multiples of 5 that we have is 403, right? Simply divide 2017 by 5 and get the quotient as 403. And also discarding the first three numbers, so 1 to the power 1 factorial, 2 to the power 2 factorial, and 3 to the power 3 factorial. So we are discarding total of 406 numbers. So 2017 minus 406, we are left with 1611 numbers. Now these 1611 numbers are neither multiples of 5, I should not say neither, I mean, they are not multiples of 5, and they have powers which are multiples of 4. So basically these numbers would leave a remainder of 1 each. So 1611 numbers leaving a remainder of 1 each, a total of 1611. So if we further divide this by 5, we get a remainder of 1. And these 403 numbers have a remainder of 0. So that is not a concern. So only thing left to be checked is the first three numbers. So we have 1 to the power 1 factorial, 2 to the power 2 factorial, and 3 to the power 3 factorial, which is 6. So these three numbers, all we have to do is check the remainder. Now if you check the first two, 1 to the power 1 plus 2 square, which is essentially 5, that leaves no remainder. So what we have is 3 to the power 6, which is nothing but 3 square whole cube, and 3 square whole cube is 9 cube. 9 when divided by 5, we can also say the remainder is minus 1. So minus 1 whole cube leaves a remainder of minus 1. So if we check all of these numbers together, we get a remainder of 1 from this set, 0 from this set, and minus 1 from the first three numbers. So that is essentially a remainder of 0. So what we know now is n when divided by 5 leaves a remainder of 0. This is the first part. Now the second part, we have to divide n by 9. So again doing the same thing. We already know that the Euler of 9 is the Euler function, by the way. Euler of 9 is 6. So again, if we have a raised to a multiple of 6 divided by 9, it should leave a remainder of 1 when a and 9 are co-prime to each other. And when would a be co-prime to 9? when a is not a multiple of 3, right? And if we also check the multiples of 3, what are those? I mean, in this scenario, we have 3, but that is raised to 3 factorial. We have 6, that is raised to 6 factorial. We have 9 raised to 9 factorial, and so on. Now, see, 3 square is 9. So any power of 3 which is greater than or equal to 2. So 3 square, 3 cube, 3 to the power 4. Each of these would be divisible by 9, right? So even 6 square, 6 cube, 6 to the power 4, these would be divisible by 9. So each of these numbers, we can say that they are divisible by 9. So again, in this case, we have a grand remainder of 0 from the multiples of 3. So multiples of 3 again, so 2017 divided by 3, there is a total of 672 numbers, again the quotient in this case. So 672 numbers leaves a remainder of 0. Again discarding the first two, that is 1 to the power 1 factorial plus 2 to the power 2 factorial, these two, we discard of two numbers. Now again, I'm sorry, I forgot to mention this. I mean, why am I discarding only these two numbers? See, remember this Euler of 9 is 6. So 3 factorial itself is 6. So 3 factorial onwards, if we check any number, they would be, I mean, any power, they would be definitely multiples of 6. 4 factorial, 5 factorial, each of these would be multiples of 6, because 4 factorial has 3 factorial in it, 5 factorial has 3 factorial in it, and so on. So again, discarding just these two numbers and these multiples of 3 that we have, so what we are discarding is 2017 minus 674, and if we discard these numbers, we are left with a total of 1373 numbers, right? So these 13, I'm sorry, my bad, 1343 numbers. So these 1343 numbers must leave a remainder of 1. Each of these numbers, same logic as in 5. And what about these two numbers? So we have 1 to the power 1 plus 2 square, which is essentially when divided by 9, leaving a remainder of 5 itself. So let me do this. I mean, we could have divided this by 9 itself, but let me just add this 1343 by, add this 1343 and this remainder of 5 together. We can do it in this way also. So what we have is 1348. Now, I hope everybody is aware of the divisibility rule of 9, right? So 1 plus 8 is 9, take it off. So what we have is 7 as the remainder. So this number, when divided by 9, is leaving a remainder of 7. So now let us combine these two. So what we know is n when divided by 5 leaves a remainder of 0. N when divided by 9 leaves a remainder of 7. Now what we need to do is essentially find the minimum possible number which satisfies these two conditions, Chinese remainder theorem. So if we do this, we get the remainder under 45. So this is simpler, right? I mean, only multiples of 5 are allowed. So let us go with this series. So we have 7, 16, 25 and so on. So 25 is the least possible number, which is a multiple of 5, as well as when divided by 9 leaves a remainder of 7. So what we can say is n when divided by 45 must leave a remainder of 25. So thank you for this. This is the answer. For any further videos, you can log into Mathatory and we will try to provide as many video solutions as possible. So thanks again. Have a nice day.